And today our speaker is Alexander Weiß from Leipzig University. It is a joint talk with Professor Max von Renessy from the same university, which is called Strong Feller Regularization of One-Dimensional Nonlinear Transport. Okay, please.
Thank you very much for your kind introduction. Let me, begin. So before we start with the actual strong Feller regularization, we will talk about the model that we were looking at, which will be pretty familiar to many of the people here, and it is done on the torus. Therefore, I will firstly introduce some calculus on the torus and a transport equation. Then the mathematical model we considered, which is a SPD with reflection, and show well-posedness for this. And then in the end, we will show some good results for the semigroup, including the strong Feller regularization or the strong Feller property. Okay, so now the introducing idea is that when you're purely looking at ODEs, they always give you a transport equation, and the transport equation doesn't have good regularity properties, as we know, and adding noise to this improves the regularity. For example, it can force the equation, first of all, to be well posed. So this is one part of the regularization by noise. But as in our case, it can just regularize the properties of the semigroup. And I will give a small and silly example for this. First, consider this very simple ODE over here, which is just, constant. And the semigroup induced by it is obviously not strong Feller or continuous whenever f is not continuous. However, if we add noise to the situation, it is very well known to everyone here that we get the heat semigroup, which has very good regularizing properties, and moreover, if f is bounded and measurable, then pt of f is smooth. And this is something we want to achieve, but we don't want smoothness. We are already satisfied with the strong Feller property, which only gives you continuity. Okay, so in order to do this, we will work on the torus. So we will actually look, on the torus, and I want to introduce ODEs on the torus. We will identify it by R to Z to make things simple, so we don't have to consider Riemannian manifolds. And, assume that B is a function from R to R, which is Lipschitz and bounded, and one periodic. And then consider the following equation. So this is just a normal ODE. Due to the periodicity of B, one can deduce the following property here, which is equivariance. And therefore, the solution X can be identified as a process on the torus because it is an equivariant function. Continuous equivariant functions from the torus to the torus can be identified with, from R to R can be identified with functions, continuous functions, which map from the torus into the torus. So this is how we will look at ODEs on the torus. Do my slides switch?
Yes.
Okay, yeah. Now, sorry, my laptop seems to be a bit slow today. So moreover, we will also want to consider measures on the torus. So consider the space, or denote the space of periodic measures by P2T, which are measures on R, such that on every slice of length 1, the measure is equal to 1. So it is a probability measure on every interval of length 1. And well, it has this periodicity property such that whenever you translate the set on which you measure by 1, then the measure will be the same. And this holds for all A in R and all sets in the Borel algebra. We shall equip this space with the Wasserstein-2 distance, which is defined as follows. So here we have the normal infimum over all couplings. And then we look at this special distance here, which is the normal distance on the torus. So if we, look as how we identify the torus as this quotient, then this is just the quotient space norm. Or distance. It is the quotient space distance, sorry. Okay, and then this space is a Polish space, complete separable space, and it's the 2 Wasserstein space on the torus. Now, we will also consider function spaces on the torus, and there we can keep in mind the following rule. So a function space on the torus is always functions from R to R, which have the corresponding property, as in this case, continuity and differentiability, and they should be one periodic. And the same for the space L2. So we have periodicity, and on each interval of length 1, the function is square integrable. Okay, and then we will have this notation here. Without any further notice. All right, so our mathematical model, or our journey, begins actually from equations with interactions on the torus. And equations with interactions are very well known here, so let me just emphasize that everything is as usual in R, in the one-dimensional space R, but we also assume that our coefficient for each mu is one periodic for all periodic measures. And also B should be Lipschitz and bounded with respect to both distances here to R and the Wasserstein space, but on the torus. Now, this equation, so we are interested in the measure-valued process from this equation because it induces a transport equation, a nonlinear transport equation, which we in fact want to regularize by adding noise to it. So the transport equation just simply looks like this, just a normal transport equation. And yes, we want to add noise such that the semi-group of this regularized equation becomes Strong-Feller, but the problem is that the Wasserstein space is nonlinear, and in the one-dimensional case, we have the advantage that we can identify the Wasserstein space with a space of functions, with a space of L2 functions. And for this, let me quickly emphasize that in one dimension, the convex set of right continuous increasing square integrable functions is isometric to the Wasserstein space. This we can exactly do by identifying the measures with the inverse cumulative distribution functions. And to mathematically define this, define the space G1 as all the functions f from R to R such that they are right continuous increasing and they should be equivariant, then this lemma here by Max von Renesse and Karl Theodor Sturm says that the space G1 is isometric and bijective to the Wasserstein space. So in other words, it can topologically be completely identified with the Wasserstein space. And the bijection function looks like this. We map a function. I write it as G mu because this should be the inverse cumulative distribution function. And we map this to the push forward of the Lebesgue measure. And this, in fact, as we all know from probability, from the first course in probability, that this gives the measure mu. And the distance we identify on this set is as follows. So it is basically an L2 distance of these functions, but since we are on the torus and everything is periodic, we have to take the infimum here over all possible translations in Z. And, well, isometry then implies, so this is part of the result, and the isometry applies that this integral here, or this distance here, is equal to the Wasserstein distance. And with the help of this, we will, well, not only with the help of this, we will try to identify we will try to regularize our equation by adding noise. Okay, so first of all, we will need to derive an equation for these inverse CDF functions, or, well, CDFs. And for this, consider f mu or f mu 0 to be the inverse CDF corresponding to the initial measure. So sorry for the confusion. This should be a mu, not mu 0. Then mu t, as in the case of equations with interaction, can be written like this as the push forward of the flow. But now we can rewrite our initial measure with respect to the Lebesgue measure pushed forward with the inverse CDF. And then this concatenation here still stays active. But this can be rewritten in the following way. So we actually push forward the Lebesgue measure by x mu and the inverse CDF inserted into the function. So what we will actually get, so this will be then our inverse CDF of mu t, and this is nothing else but the solution to the equation, but perturbed by the initial values which come from the CDF of the initial measure. And, well, we will see what this means. So actually, this function ft mu does solve the exact same equation with interaction with the initial measure lambda, but we start the process in the initial measure. Well, we don't start it in the identity, as in the case of as in the case of equations with interaction, but we started in the inverse CDF of the initial measure. So here nothing very complicated happened. And now we have the problem that these functions, in order to regularize them properly, one, first of all, needs to add elliptic noise. So this, in this case, would be space-time white noise, because, well, this is typically how you regularize or can regularize by adding noise. You really need elliptic noise. And moreover, we need to guarantee that our ft mu actually stays an inverse CDF. So it needs to be increasing, and this is not possible by only adding noise to the equation, because the noise might perturb the solution in a way such that it is no longer increasing, an increasing function. And so this ansatz has been attempted with success by De La Rue, Hammersley, and De La Rue and Ouknin, where they, in the De La Rue Hammersley paper, showed a regularization happening, but without a nonlinear term here. And in the De La Rue Ouknin paper, they proved existence of such solutions with regularizing, well, with added noise, and they added Laplace, but they couldn't show any properties, any good properties for the semi-group. And therefore, we will try something else. So, first of all, we need to differentiate this equation with respect to the spatial variable, and then we will denote the derivative by g, and we get the following equation. So here, the situation will be easier, because when we had to ensure an increasing function up here, and the situation down here is way easier, because here we only need to guarantee that it stays positive, and this is already very well known theory of reflected SPDEs. And as we see here, we want to write this equation into a closed equation. So for this, we need we basically only need to rewrite ft mu in terms of gt. This can be easily done. Consider a general function f and its derivative g. Then we can write the difference here by just the integral of g. Sorry. And, well, we can then write fu as this integral here plus the mean value of f with respect to the Lebesgue measure. And therefore, we will denote this whole operation here of getting from, transforming a derivative into the actual function. We will denote this by this function a, which stands for antiderivative. And we always consider this for one periodic functions g, because when f was equivariant, then the derivative must be one periodic. Therefore, we can rewrite the equation now in this following form, where we add this additional term for the mean value. Well, and this is basically a closed form of the equation, which we can now regularize. Now, this is the regularization which happens. So first of all, the most important part is adding here elliptic noise, which in this case here is space-time white noise. Now, since space-time white noise has very bad regularity properties, and we want our solution to be a function, or well, at least we want our solution to be something good, we also need to add a Laplace operator so it counteracts the bad regularity properties of the space-time white noise. And moreover, we add in our function above a measure eta, which should guarantee the reflection. So it should guarantee that our solution stays positive, and this is the reflection measure, which is very important. Well, and the rest, so GT should be positive, and it should be periodic. And our initial condition should look like this. So positive and just something in R. And the space-time white noise is more precisely denoted like this, as usual, where EK is an orthonormal basis of L2. L2 over the torus. So sine, cosine. Okay, so now we have written down this equation. Then obviously we need to write down what does it mean to solve this equation, what does it mean to be well posed. Now a triple G, M, and eta is called a solution to the equation if the pair GM is continuous and adapted, and G is non-negative such that it is also periodic for all t. Moreover, we define the solution property in a distributional way via test functions. So in order for it to be a solution, we need for all t greater than 0 and test functions phi. We need to have this equality here where, well, in the first couple of terms, it's just as you are used to it from normal PDE theory or SPDE theory. And then in the end here, we have this additional term which comes from the reflection measure. So we integrate the function phi with respect to this reflection measure. Oh, sorry. Okay. And the solution to the mean value process should just be as usual, just a solution to an SDE. Now, moreover, the integral of our process G over eta should be equal to 0. And, well, this can be easily seen why this makes sense, or should be the case, because eta plays the role of pushing our solution upwards as soon as it starts hitting 0. So whenever G is positive, eta sleeps. But as soon as G starts approaching 0 and really tries to flee this positive half plane, eta wakes up and starts pushing G back up. So the integral, the measure eta should only have support where G is equal to 0. And where G is positive, eta shouldn't do anything because it didn't have to do anything. It had nothing to do. These are reflected, so-called reflected SPDEs, and they can be made very general. So we have this special mean value term here, but if you just omit this, then you can just write an SPDE like we have written here, very general. And this is well-known theory. And they have been studied by Nuala and Pardue, Donati Martin and Pardue, and by Tusheng Zhang and Xu. And we can therefore rely on already existing theory in order to solve these. So first of all, show well-posedness to these equations. And our well-posedness conditions are that the function b, first of all, it must be differentiable. And we also assume that b and b prime are Lipschitz and bounded. Then there exists a unique solution triple for every initial condition, and here is a very important part. So this only works, so we can only solve it for positive continuous initial conditions G. And then the solution will also be continuous, but we really only have this well-posedness result for continuous initial conditions. Later see that as our obstacle in this obstacle problem, we will choose the stochastic heat equation. And then we will get the end result. But first of all, let me state this. So let V our obstacle be continuous and periodic, such that at initial time 0, the function v is positive, non-negative. Then there exists a unique pair z and eta, such that z is periodic, z is greater or equal than minus v, or in other words, z plus v is greater and equal than 0. And z should start at 0. So then this property here also makes sense, because if z is 0, then here at initial time t, then obviously it is greater or equal than minus v, since it has been chosen to be non-negative. And eta is a measure, and we have this solution property here as before, but it is much simpler, because here we only look at a deterministic obstacle problem, which is linear. So we only have the Laplace operator involved here. Okay, and then here we also have the same property as before. Zt plus Vt should be equal to 0. Now, this lemma was proven by Nuala and Pardue, and this is they actually proved that the solution to this exists and is unique. And I will give a little bit of a proof for this, or an idea for the proof, so you understand it a bit. So they look at PDEs like this, Zt epsilon, where it is the solution to a heat equation plus this perturbation part, where this minus is equal to the negative part. And later, they consider these PDEs, and then they prove that they converge to 0 as epsilon approaches 0. And to see why this actually should give the correct thing, if you let epsilon go to 0 in this equation, then this 1 over epsilon part explodes. So in order to have something meaningful in the end, this here must be equal to 0 in the limit. And this implies that this limit term here plus the obstacle are equal to, well, are non-negative. So this is the intuition behind it. In the end, well, they proved that epsilon converges, and 1 over epsilon here converges in the sense of periodic distributions to a positive distribution, which will give us a measure as a limit. So actually the limit of this for epsilon to 0 is the reflection measure. Okay. And they also prove some estimates for the solutions to these equations, but they only prove them for the infinity norm, so the sup norm. And the first property is that the sup norm of the solution is less or equal than the sup norm of the obstacle. And here we have a similar estimate for differences. And these will help us in order to apply a Picard iteration argument for the solutions of our SPDEs with reflection. Now, here comes the idea of the proof for SPDEs with reflection. We will use the preceding lemma, and as an obstacle, as I said, we will choose solutions to just the normal nonlinear stochastic heat equation. So we start at our initial points, and then we define this iteration here, well, with respect to the previous solutions always. And then with these ftn's, we should consider the solutions zn's to the deterministic obstacle problem, with the obstacle being the heat equation. And then our solution will be the limit of this gn, which is zn plus fn. With this, we can do a Picard iteration, because for the stochastic heat equation in one dimension and our obstacle problem, we can get good good estimates which are important for the Picard-Lindelöf result with the help of this lemma here, which gives us continuity with respect to the obstacle. And since the obstacle is a stochastic heat equation, we will only need estimates for the stochastic heat equation in the soup norm, which are possible to achieve. Okay, now we get the result, and for the solution to our equation, we can get one standard and one a little bit non-standard result. Continuity with respect to continuity with respect to the initial condition. And here for GT, we can get this estimate here in L2, which is standard for all x, by the way. But we cannot get a good Lipschitz estimate here because in our equation, we only have, so let me go back to the equation. We only have local Lipschitz coefficients, because here we have GT multiplied with a Lipschitz function, which is bounded, but so this GT here is not bounded, therefore unbounded Lipschitz functions which are multiplied give you locally Lipschitz functions. Therefore, we cannot get standard estimates, and we need to work with a stopping time here to get a good estimate, and we will later also use this estimate for our final result. Now let's get to our main results. The first one is that we prove that the function PTF, which is defined down here, is a semigroup. PTF is not a semigroup. Well, it is a semigroup, but this is not what I wanted to say. The function PTF from the space of continuous functions in the L2 topology times R to R, which is defined as follows, can be uniquely extended to a continuous function P tilde TF, and it is locally uniformly continuous, which is, since this is for any f in with bounded for any bounded f, this is a strong Feller property. We will later then enlarge the semigroup to the entire space L2, positive L2 functions, and then we will actually get a proper result, a proper strong Feller result. But before we come to that, I want to actually prove this theorem, because I think the proof is very interesting. And it is based on a coupling argument, which has been carried out by Wang multiple times. Here in his book, he has a lot of applications. And I will illustrate this with one-dimensional SDEs, so everybody understands it. And then in the end, I will say it works in exactly the same way for SPDs, even though this is not true, but it is very similar. Not exactly the same, but very similar. Okay, and so let's first of all choose U and V and R such that they are different, and consider the normal system of SDEs here, where A is Lipschitz and bounded. What we want to prove is that they are strong Feller, so the induced semigroup is strong Feller. And in order to prove this, we will use a coupling argument, and this is the coupling equation. So x tilde starts at V, and well, here we have the coefficient from here, so the U here is not a typo. This is actually, and the X without tilde is not a typo. This is actually what I wanted to have. And then we add here a term which forces X tilde to be equal to xut at time capital T, where capital T is fixed. So we started at V, and then at some point we forced the system here to target our solution xut and also reach it at time capital T. So if we define it like that from Ito's formula, we can see that most of the terms cancel out. And we only stay with this term here. Then from Grünwald's inequality, we can deduce the following inequality. And therefore, for time capital T, so I'm omitting a bit of, I'm omitting some details because this here is singular at time capital T. So in theory, this is not well defined. It is only defined up until time capital T, but you can overcome this problem and just believe me that we can define this x tilde vt to make sense at time capital T, and by this inequality here, we can prove that since this integral will be equal to infinity when it goes up until time capital T, we can prove that they must be the same almost surely. So we have achieved our goal. Now we will denote xi t by t, we will denote t minus t by xi t. And by Ito's formula, we can then get this inequality here, where one part comes from this equality and the other part comes from differentiating 1 over xi t. Then in a simplified form, we can estimate this by this term here. And 2 plus xi prime t is nothing but 1. So this is just written in a complicated way. Now, if we integrate this, both terms, these terms, and we add this integrated term on the left-hand side and this integrated term on the right-hand side, so here I have forgotten an integral, we can prove that this term here is finite, this integral. So when 1 over xi t wasn't integrable, but this term will be integrable. And this is important because this will be in our Gazanov density, and it is important for the Novikov condition. So this is one thing why it is important. Now note that x tilde can be rewritten as this equation here, where here now we inserted x tilde plus some ominous b tilde t. So what does b tilde t look like? First of all, it is plus minus this a term, and then plus this term over here. Now, from what we have shown before, by the Novikov condition, we can show that the Gazanov transform here makes sense, and therefore this b tilde t is a new Brownian motion under the probability under a new probability measure q with Gazanov density looking like this in the usual form. I'm sorry. Then we start showing the strong Feller property now. So we assume that f from R to R should be bounded and measurable. Then by weak uniqueness, we can first of all get that f of xvt here is equal to expectation q of x tilde vt, because x tilde and x have the same distribution well, x tilde under Q has the same distribution as x under P, and x tilde of V of capital T is actually equal to x ut. So this we can then just rewrite as x ut, and then this difference here only becomes relevant for the difference of the measures Q and P. So this difference will be less or equal than the infinity norm, with the sup norm of F, times the total variation of P and Q. And by the Pinsker inequality, we can estimate the total variation by the Kullback-Leibler divergence, or the entropy. Now, the Kullback-Leibler divergence, or the entropy here, is the logarithm of the density, but our density has exponential form. And if we look, well, what it looks like, so if we apply log here, then we have some martingale parts which will equal to 0 under the expectation, and these parts we can estimate with respect to the initial conditions to get the following here. So here we actually have shown strong Feller property, not only this, but we have actually shown that it is Lipschitz continuous. And we want to show exactly the same for our, well, coupled system, but the problematic part is the SPDE part. And because there we have this measure term with which we cannot really work, or if we take the difference of two different solutions with different measures, then we cannot really estimate them. But we can use a little trick. I'm sorry, I'm a little bit sick. So we first of all fix the nonlinearity coefficient here, which we had in our solution. And then we approximate the SPDE with reflection with SPDEs of this kind. Now, you may ask, why did I fix this coefficient over here? Because we use a result of Donati, Martin, and Pardue, where they show that these converge to a unique solution, but they do not show it for SPDEs where the nonlinearity is of a functional type. But rather, you can only insert, well, the coefficient can be of a type where you insert it into a function. But here, obviously, we insert the entire function. So this is of functional type. Therefore, we have to overcome this problem by fixing this coefficient. But for random coefficients, they still proved existence and convergence of these solutions. And then we have that these solutions converge to what we want, to our solution, almost surely, and in LP. So in every shape or form, this convergence happens, which is very nice. And we will then use this coupling method on these approximation SPDEs, but a major problem is we have this locally Lipschitz part here, which gives us some bad terms. And I will, well, not bore you with the exact computation, but if we fix this stopping time here, then we can do a similar estimate as we did before, but we have some ugly terms in between, which come from the non-existing, from the local Lipschitzness. And we therefore also not only get, we don't get Lipschitz continuity, but only continuity. So from this inequality here, by duality, since it holds for all f, for all continuous f. Remember, we first show all this for the epsilon approximations, and then we let epsilon go to 0. Therefore, we need f to be continuous, and therefore it holds for all continuous. But then, since the total variation is the supremum, well, a supremum of an integral over continuous functions with norm less or equal than 1, we can show that the total variation of our semigroup operators here are also less or equal than all these terms. And now we can make all these terms very small if x and y and phi and psi are very small, because we can control these probabilities here and this expectation. Now, note that from the lemma where I showed estimates for the solution to the reflected SPDE, we have such conditions. And this, by dividing by n, we can choose n so big that it becomes as small as we want. And moreover, here, if we put the supremum over all phi, which have L2 norm less or equal than some fixed m, then we can make this term smaller or less or equal than epsilon over 2. Then we can choose delta epsilon in a smart way, so it will be exactly this way. Such that we can, go through the delta epsilon argument for uniform continuity, but only on this ball with L2 norms less or equal than m. And we can therefore uniquely and continuously extend the function on all balls and on all balls here, and therefore we can extend it to the entire space L2, and the extension will also be continuous, but only continuous, no more regularity. Then we also had some quantitative results. So first of all, with everything we have shown, the Markov process can be extended to a Markov process. So here we had a Markov process with initial conditions in the continuous functions, because remember the positiveness result only was possible when the initial condition was continuous, but you can extend this to a Markov process, to a good Markov process on the entire L2 positive functions. And this Markov process will be, in general, a strong Feller process. And moreover, we can find an estimate for the total variation, or the Kullback-Leibler divergence, or the entropy of the two semigroups with respect to the distances of the initial conditions. So rho here is the distance of phi minus psi and x minus y. And whenever rho goes to 0, then this term here also goes to 0. And this estimate can basically be achieved by choosing n in a good way in this inequality. So making a particular choice for n, and in these summons, they come from a Cauchy-Schwarz inequality, which is done in the proof. But if you do, instead of the Cauchy-Schwarz inequality, the Hölder inequality, and optimize with respect to the Hölder parameter, then also make an explicit choice for n, you can get such a quantitative result for all theta in 0, 1. Moreover, since we have started differentiating our equation in the beginning, so here we had one-to-one identification with the Wasserstein space, but here we have lost the correct topology in this space here, which is 1, small problem or letdown, but in the end, we have shown strong Feller property for this regularization, not in the correct Wasserstein topology, but in a slightly different topology. So we only considered the space of measures such that the inverse cumulative distribution functions are in H1. And we equip this metric instead of the Wasserstein metric, we equip it with this metric of differences of the mean values and L2 distances of the derivatives. Then we get that the family of solutions induces a unique Markov process here on this space. And the following map here is continuous and locally uniformly with respect to this metric here. Okay. And well, this was my talk. Thank you very much for attention. And
Okay,
I'm ready for
thank you very
questions.
much for interesting talk. And maybe somebody have questions or comments, please. Alexander, you mentioned that you modify topology in the space of measures. What can you say in this topology? For example, if I take discrete measures, will they still be dense in this space or not?
But he needs for CDFs to be smooth.
Yes. This is the problem.
He needs only to start with smooth if to look for this property. I think that formulation does not require smoothness, or it does.
So the initial conditions are such that the CDF is smooth. So we only look
I
at the
see, I
space.
see.
Yeah.
You see only for smooth measure. You look only for smooth measures.
Yes, yes. For
Mhm.
simplicity, only if we look at measures which are absolutely continuous with respect to the Lebesgue measures. So you can think of them.
I am just looking for some natural final. Okay, I understand. So your regularization acts on this smooth on these densities, making it more smoothly. Am I right?
Sorry, I don't understand the question. So we only look at this dense subset of the Wasserstein space.
Yes, I understand. But then you said we need only we are working only with smooth measures. Yes.
Yes, yes.
Okay. So this measure has density with respect to the back measure on this one-dimensional torus.
Yes, yes.
Okay. What happened with this density during the evolution?
Well, the density still, well, we still have a density. We didn't study we didn't study the evolution of this density, to be honest. So I cannot really say this.
But you did some regularization. And I'm trying to understand what kind of random measures do you get from as a solution. For example, suppose that at time 0 we have a density like this one. Let me. We have density like this one. Here is our circle, and density was like this. That's all. Then at time 0. Then
Yes.
at time t, of course, it is random, but do we have density like this one, which is positive everywhere, or we still have such kind of density which just rotate in some directions?
This is actually a really good question. So I cannot come up with an answer from the top of my head because the relation between the measures and the actual process that we have is pretty complicated. So to get a measure from our solution here, so first of all, we need to apply this A operator. So we need to look at, let me maybe see. So here we need to insert our solutions. And then we have to look at these functions here from U, and we have to push forward it with respect to the Lebesgue measure.
I see.
And so we didn't study this.
I see.
And
But,
I cannot come up with an answer from the top of my head because the relation is very much nonlinear and very complicated.
Because this question is natural, because in a linear situation, when we have Euclidean space and we have shift and diffusion, it can happen that we, when we use the smoothness, we add Laplace and so on, we just have a shift which is shift along the random trajectory. Yes, when square of diffusion, 1/2 of square of diffusion is equal to the shift coefficient, yeah?
Yes.
Then, so in those cases, we maybe have a regularization in some space of densities, but the densities evolve very simply. They just are randomly shifted. And the evolution really depends on the competition between the coefficients near Laplace and near the shift operator, near the shift. So maybe the same happened here, and it will be interesting to look at the transformation of the densities.
Yeah, I agree. Yeah, this is you can study this process and look at it. Yes, surely.
Okay, thank you. And maybe somebody else have questions or comments, please.
I didn't I didn't quite understood, but is it possible that we really start from some discrete measure and then like immediately fall into the space of smooth measures?
So no, our initial measure can't be a discrete measure. So
Georgi, actually, it is almost the same question as I asked. Yeah?
Yes.
So we only look at measures which have a density with respect to the Lebesgue measure.
Okay.
Okay. Thank you very much. And for today, that's all. And Georgi, who will be the next speaker?
You will be the next speaker.
Not me, Yasmina Georgievich, not me. Okay, we together will present something. Okay. For today, that's all. Thank you for attention and see you next week. Bye.
Okay, bye.
Goodbye.
Bye.